I don't see anybody joining it. Okay, there we go. So hello, everyone. I'm just going to give a couple of minutes here for people to get signed in as they're rolling in here, and then we'll get started with just some housekeeping items and also introductions of our speaker and our panel, and then we'll get going. So just a few more seconds here as people are continuing to join. We call this is the popcorn effect of the number rolling up. When the number starts to, when the popcorn starts to slow, then I'll I'll do the intro. But all right, so we look good. We look like it's slowing down. I'm going to get started. So hello, everybody. I'm Renee Yager, Director of Marketing at EPC, and welcome to today's webinar, GaN plus Digital Control for Ultra-Thin Designs. Before we get started, I would like to go over just a few housekeeping items for today's event. First of all, you have the opportunity to submit text questions to our presenter and our panelists by typing your questions into the Q&A feature at the bottom of the screen. You can send in your questions at any time during the presentation. We'll collect these and then we'll answer them at the end of the presentation. Also, at the conclusion of the webinar, we will select one participant at random to receive a copy of the 3rd edition textbook, GaN Transistors for Efficient Power Conversion. If you are the lucky winner, we will contact you in the next few days for your shipping information. Now, I would like to introduce our panel today. We have with us Andreas Reiter from Microchip. Andy studied physics at the University of Applied Science in Munich. Since 1996, Andy focused on thermodynamic system modeling and related hardware and software development before joining the power conversion community in 2006, focusing on the development of full and semi-digital control stages of switch mode power supplies. Andy joined Microchip Technology in 2010 and today is working as applications engineer for digital power applications. He holds several patents on control algorithms, DSP core, and IC peripheral architectures. Welcome, Andy. Okay, we also have with us today Michael DeRoy. Michael is the Vice President of Applications Engineering at EPC. He has authored and co-authored over 50 papers at various conferences and journals. He has been granted 50 US and international patents, and he is the author and co-author of 6 books. His experience covers highly resonant, loosely coupled wireless power, high-density DC-to-DC converters, GaN IC development, RF power amplifiers, solid-state high-frequency power converters and devices, utility applications of power electronics, uninterruptible power supplies, integration of power electronic converters, power electronic packaging, induction heating, photovoltaic converters, MRI systems, and gate drivers with protection features. Welcome, Michael.
Thank you.
And now, allow me to introduce our speaker today. Alex Lido is the CEO and co-founder of Efficient Power Conversion. As a co-inventor of the HEXFET power MOSFET, Alex holds many patents in power semiconductor technology and has authored numerous publications on related subjects, including co-authoring the first textbook on GaN transistors for efficient power conversion. Alex, thank you for joining us today.
Thank you, Renee. And in this webinar, we're going to show you how GaN-based solutions coupled with digital control can increase efficiency, shrink the size, and reduce system costs for high-density computing applications like ultra-thin laptops, high-end gaming systems, and high-density displays. So on the agenda, we'll first discuss how leveraging the advantages of eGaN FETs, such as their tiny size and very low losses in switching, and how that enhances the performance of ultra-thin DC-to-DC converters. And then through our work with Microchip, we'll show how combining the advantage of eGaN FETs with digital control can provide solutions to meet the demanding requirements of high power in very small form factors for ultra-thin laptops, high-end gaming systems, and displays. We'll explore multiple topology options to get thinner solutions, including a synchronous buck and a multi-level converter. And lastly, we'll look at some actual results from these designs. So as computers, displays, smartphones, and other consumer electronics become thinner and more powerful over the past decade, there's increasing demand for addressing the challenge of thinner solutions while extracting more power out of very limited space and very limited airflow. To address this challenge, we'll examine the feasibility of adopting various non-isolated DC to DC step-down topologies for an ultra-thin 48 volt to 20 volt power solution. When we say ultra-thin, we mean they are thin enough to fit inside a notebook computer or an ultra-thin display. First, however, let's ask the question, why eGaN FETs for these solutions? And this table compares a 100 volt eGaN FET with two best-in-class silicon MOSFET counterparts. The comparison slightly disadvantages the eGaN FETs because we're comparing 80 volt MOSFETs against 100 volt eGaN FETs. The eGaN FETs have much lower switching losses due to lower gate charge, lower losses due to shorter dead times, and that's achievable because there's no reverse recovery in eGaN FETs, and also lower output charge. And they're very significantly smaller compared with silicon devices with a similar on resistance. So now let's ask the question, why digital control? Well, the ultra-thin converter designs employ digital control due to its flexibility, especially in development of complex control schemes. Regulating control based on compensator controllers for current and voltage loops together with various circuit protection functions can be easily managed digitally. And the high time resolution available from these controllers allows for optimal dead time management for GaN, whose dead time can be within a few nanoseconds, is much lower than that of silicon MOSFETs and their controller drivers. Digital control also enables the use of GaN-compatible gate drivers that have high drive strength for fast switching and high side gate clamping for gate over voltage protection. The embedded MCU core is commonly used to do much more than just executing a feedback loop. Embedded self-optimizing protection thresholds, enhanced plausibility checks on measured voltages, currents, and temperatures, verification of control signals, adaptive efficiency and bandwidth optimization algorithms on the fly, which you can do on the fly between different control modes, they all contribute to the robustness and performance of a final end product. So let's look at two ways to achieve thinner converter design. And we're going to start with the simplest synchronous buck topology, which is very popular in DC to DC step-down converter design because it's simple, it's easy to control, it's low cost. Digital controllers with their freely programmable feedback loops and extremely flexible peripherals provide support for all standard and many advanced commutation techniques and control modes. Especially buck converters can operate in many different fixed and variable frequency modes. Each of them has a specific advantage and they have specific downsides, and some of them require specific auxiliary circuits or high fidelity feedback signals that influence cost. Here are 5 of the key control modes that can all be accommodated using digital control: voltage mode control, average current mode control, peak current mode control, hysteretic mode control, and adaptive constant on time. Now here's a very schematic block diagram of a typical average current mode control system comprised of cascaded outer voltage loop and an inner average current loop. This type of control system is widely used for higher power single and multi-phase converters above 50 watts of output power. The output voltage loop is comparing the most recent voltage to an internal reference value and processing the inverse of the value deviation through a discrete compensation filter. The filter output represents the current loop reference for the following current control cycle. The inner control loop compares the most recent current feedback value with the new reference provided by the voltage loop and processes the inverse of the deviation in a second compensation filter stage. Depending on the control and commutation modes, the second filter result is then either written to the PWM signal generator registers, adjusting the duty ratio, phase shift, or frequency, or in the case of hysteretic or peak or valley switching commutation, to other peripherals, such as a D to A converter, and this will adjust the analog comparators. This block diagram shows the architecture of a high-performance, safety-ready digital signal controller, the dsPIC 3364MP102, specifically designed for high-speed switch mode power supply applications. The device architecture is a modified Harvard architecture microcontroller, including a RISC central processing unit with integrated digital signal processor. Parallel memory buses and interconnected peripheral modules are also included. Inside the dashed line, there we go, is the segment of the architecture used to implement the high-speed real-time control loops, being a balanced assembly of interconnections between peripherals running asynchronously from CPU clocks and processes, such as analog comparators and event logic, and synchronized functions looping in data processing of feedback signals used to establish highly responsive, nonlinear, intelligently validated condition responses. The device itself is equipped with enhanced port protection and supports up to 150 degrees C ambient temperatures, which is about 175 degrees at the junction, and is available in packages as small as 4 by 4 millimeters, which meet typical robustness and space requirements of the most stringent high power density DC to DC converter designs. There are three major dsPIC 33C-MP switch mode power supply device families available. The one selected for the designs we presented is the dsPIC 33CK MP10X series. And this series has a small footprint, simplified peripheral set dedicated to the smallest form factor and highest power density converters with a wide range of packages optimized for integration directly on the power board. Pin count, memory size, peripheral set, and package types are all tailored to a single power stage controller. The highest efficiencies and power densities are essential technical aspects enabling end products with continuously increased performance. Reliable, freely configurable, high-resolution switching signal generation enables the adaptation of GaN-compatible gate drivers and minimizes losses by adjusting dead times with sub-nanosecond precision. Intermediate bus converters always represent sensitive single point of failures in intermediate bus architecture power distribution networks. Hence, functional safety and high robustness are vital key design aspects and translate directly into the reliability of the end product. Now, the programmability of many fundamental functional blocks like feedback loops, switching frequency, protection thresholds, remote control interfaces, and much more makes it easy for end users to integrate a fully configurable intermediate bus converter module into the power distribution network with minimum design efforts. Especially dynamic loop tuning helps to fight and solve power distribution network stability issues, leading to more balanced and robust end products. Besides its extremely high efficiency, the EPC 9153 is a straightforward, plain and simple buck converter. And we'll talk a lot about it, and we'll show how the flexibility of a digital controller was used to solve three key application challenges. First, improving light load efficiency. Light and no load conditions, the efficiency of synchronous buck converters drops dramatically, which becomes a challenge when used in computer infrastructure systems where high performance loads mostly step between light and full load conditions. The digital controller allows the detection of either discontinuous or continuous mode transitions and can modulate the synchronous rectifier switch as an ideal diode to minimize losses. However, asynchronous operation would result in significantly reduced response times, which is counterproductive, considering that the load profile will continuously demand high speed response from the light load. Second, a better way is to switch between variable frequency hysteretic mode at light loads and fixed frequency at higher loads, which both have similar response times. In hot output standby mode, the converter needs to provide a regulated output voltage at no load to support downstream load devices to instantly recover from sleep modes. As hysteretic mode can be established by driving the switching cell by hardware comparators triggered on valley and peak currents, only a minimum of control loop intervention is required to provide a stable output voltage. During this period, even the CPU core can go to sleep, only woken up occasionally when the independent peripherals indicate a change in load. And third, overpower boost mode. The requirement for supporting so-called boost modes, output power above the nominal maximum for a limited amount of time, is common in computing systems where occasional peak power demands are significantly higher than the average power consumption of loads, and where the low probability and short duration of overpower events doesn't justify an over-designed power distribution network. Now, the EPC 9153 that we're going to look at can support up to 200% of its nominal output power of 250 watts for a limited amount of time. And the example firmware, it currently defines two duration thresholds, one at 150% and a second at 200% load. And this implementation is really for evaluation purposes only. In a real-world application, the overload limit would have to be dynamic and adjusted to the application environment, where thermal management is the main limiting parameter. So let's look at it. Here's a photo of an eGaN FET-based synchronous buck converter, the EPC 9153. The 100-volt rated eGaN FET, the 2218, was just introduced a month ago as an RDS-on of 3.2 milliohms, and it was selected for this power stage. The UP1966A gate driver that features high drive strength is used to drive these FETs. The synchronous bootstrap circuit with the EPC 2038 are little tiny devices, and they ensure that the 4.9 volt gate voltage is used for the high side drive. The DS-PIC33CK device is used to drive and control the converter in a fully digital fashion, where the feedback loops are implemented and executed in software. Now, the maximum component height of the EPC 9153 is only 6.5 millimeters. The total system efficiency at 48 volts and 56 volt input and 20 volt output are shown in the graph on the left versus output current. At 20 volt output, peak efficiencies reach 98.2%. The thermal image of the synchronous buck converter operating at 56 volt in to 20 volt out at 12.5 amperes and at thermal steady state with a heat spreader and 400 LFM of forced air is shown on the right. The maximum temperature on the board is less than 62 degrees Celsius with a 25 degrees C ambient. The second topology, the multi-level converter, can achieve the same inductor current ripple as a synchronous buck converter with lower switching frequency and inductance. This offers the benefit of reduced switching loss and inductor and system size. The operating principle of a three-level topology used to design an ultra-thin converter is shown here. The switching events are at less than 50% duty cycle. Q1 and Q2 have the same duty cycle and are shifted by 180 degrees in phase. Q1 and Q4 and Q2 and Q3 are complementary respectively. The switch node voltage and inductor current are shown at the bottom two waveforms. When Q1 and Q3 conduct, the flying capacitor and output inductor are charged up. Q1 turns off, Q4 turns on, the output inductor freewheels through Q3 and Q4, Q3 turns off, Q2 turns on, the flying capacitor charges up to the output inductor, and last, Q2 turns off, Q3 turns on again. Current commutation always happens between Q1 and Q4 and Q2 and Q3. In this way, the frequency, you can see the frequency at the bottom at the switch node is twice the switching frequency. And that's very important because that sets the inductor size. To design this 40 to 60 volt input, 5 to 20 volt output voltage 3-level converter, eGaN FETs are used to further reduce the converter size and improve efficiency. A 100 volt 3.5 milliohm eGaN FET is chosen for Q1, as this device needs to block the full input voltage for a short period during the startup. 40 volt 3.5 milliohm eGaN FETs are used for Q2, Q3, and Q4. The converter is switched at 400 kilohertz with the 2.4 microhenry inductor, seeing a frequency of 800 kilohertz while producing a 12.5 ampere max current output. Similar to a standard buck converter, the flying cap multi-level converter control scheme needs to implement output voltage regulation and output current protection in order to avoid overstressing any FETs. The flying capacitor multi-level converter controller also needs to maintain the voltage balancing of the flying capacitor to half the input supply voltage during normal operation and startup. Now, during startup, the flying capacitor is initially charged to half the input voltage using the existing voltage sensing resistor network, plus an additional resistor located between Vin and the VCP, or the capacitor voltage, and turning on only Q4. Now, if you're interested, more information on this control methodology can be found in the paper that's referenced in the lower left-hand corner of this slide. The main control loop of this design is based on a digital average current mode control loop. This loop calculates the required duty cycle of the buck converter plant to meet the power demands in the next switching cycle. Due to the frequency doubling effect of the flying capacitor operation, a switching cycle is defined by the 400 kilohertz base switching frequency. Hence, each new control output will remain constant during one full flying capacitor period and 2 inductor current ripple periods. The flying capacitor voltage balancing algorithm continuously calculates the PWM edge offset required to compensate for asymmetries in the capacitor voltage caused by the component tolerances, temperature effects, and overload. The output of this additional control block is incorporated into the PWM control output of the main loop before new timing is rolled out by the PWM logic. All fundamental benefits of embedded digital control in GaN-based intermediate bus converter applications mentioned on the previous slide still apply to the EPC 9148 multi-level power converter. In comparison to the EPC 9153 buck converter that we talked about earlier, where digital control can help significantly to increase performance and make the design more efficient and robust, the multi-level circuit of the EPC 9148 essentially requires the enhanced capabilities of complex signal generation and interconnection loop control to work at all. Now, 2 key aspects stick out. The precision timing of the doubled half-bridge drive with pulse time steering capabilities is required for balancing the flying capacitor voltage. Additionally, the flying capacitor voltage balancing requires independent control algorithms deriving and providing parameters from the main control loop as well as peripheral instances. Notably, the flying capacitor voltage control can become a significant performance bottleneck if not tightly coupled to the main control loop and peripheral operation. At the high ripple frequencies of 800 kilohertz or even higher, the process coordination between PWM signal generation, A to D converter triggering, main loop output modulation, and balancing parameter calculation needs to be highly deterministic and with very little jitter. Here's a photo of the 3-level converter. The 100-volt rated eGaN FETs, the EPC 2053, with the RDS-on of just 3.1 milliohms, is selected for the power stage. All components, including controller and current sense, are on the top side of the board, and the maximum component height is only 3.5 millimeters. The total system efficiencies at 48 volts in and 12 volts out and also at 20 volts out are shown in the graph on the left versus output current. At 20 volt output, efficiencies reach nearly 98%. The thermal image of the converter operating at 48 volts to 19 volts with 12.5 ampere output current is shown in the right graph. The maximum temperature on the board is less than 65 degrees C with a 25 degrees C ambient. This converter is highly efficient and could carry even more current with some more forced air. Whereas the two converters that we talked about, the 9153 buck converter and the EPC 9148 multi-level converter, achieve approximately the same efficiency, there's a significant difference in the final system size. Here's a comparison of the two converters showing the distinct size advantage of the multi-level converter. In addition, the multi-level converter is only 3.5 millimeters thick compared with 6.5 millimeter thickness of the buck converter. In summary, the combined advantages of eGaN FETs and digital control provide ultra-thin solutions to meet the demanding requirements of high power and small form factors for ultra-thin laptops and high-end gaming systems. Digital control provides the flexibility to simplify complex control schemes, and it also provides the resolution to enable optimal dead time management and the high drive strength for fast switching, as well as the required protections. The 48 volt input stage for these applications require 80 to 100 volt rated devices. In comparison to silicon MOSFETs, the eGaN FETs provide superior performance, smaller size, and lower cost. GaN plus digital control is the solution for the 48 volt revolution. For more detailed information about eGaN FETs and ICs and 48 volt DC to DC applications, visit us at epc-co.com. And you can also purchase the EPC 9148 or EPC 9153, as well as many other reference and demonstration designs on our website. And for anything about the 48 volt DC applications involving digital control, please visit Microchip at microchip.com. Thank you very much.
All right, thank you, Alex. So we are going to start answering some of the questions that were submitted during the presentation. As a reminder, you can continue to submit your questions through the Q&A feature at the bottom of the screen. And so let's get to our first question, which is, how do you properly measure the temperature of eGaN FETs with thermocouples?
Boy, I think Michael's good at that. How about give me a shot at an answer there? You spend all day long stressing about that.
You can get some very small thermocouples, basically about 48 gauge wire or even thinner. It is always tricky to measure them in circuit. It is a good idea to properly insulate them from the FET, but still get them as close as possible. If you're measuring the low side device, the substrate, which is the silicon that the device is made on, is at the source potential and ground, so you can get it pretty close there. One thing that you need to be aware of is that as you're putting thermal material between the device and whatever cooling system you have, there is still a thermal path with resistance in there, and that will offset your data. When it comes to measuring temperature, we like to use multiple methods simultaneously so that we can see what's going on, particularly when you're using a heatsink. Thermal cameras, where you paint the backside of the die with a matte black paint, helps to improve the emissivity and give you a more accurate reading. And we find that using that in conjunction with the thermocouples, we can get to temperatures within 1 degree C of each other.
And I would like to add that Michael and his team have done some amazing work with thermal management, and we can now show how you can get a 4 square millimeter die down to 4 degrees C per watt with pretty simple thermal management techniques. And there's been a lot of improvement lately in thermal gels and thermal insulating materials as well.
Yep.
Great. Okay, the next question is, can we use GaN devices at a frequency around 150 megahertz in a hard switch synchronous buck converter? What's the maximum switching frequency achievable using GaN devices by EPC, and what can be the problems with that?
So our GaN devices will switch very fast. As a matter of fact, we've challenged Steve Sandler to measure the switching speed, and he's actually documented transition times of 140 picoseconds, and that was the limits of his measurement probe at that time. So the switching speed is about as fast as you want it, but of course it takes very, very careful layout and driving in order to get those. The record that we have right now for hard switching is 75 megahertz. It's a buck topology running at 75 megahertz hard switching, and it runs about 92% efficient. So obviously you can manage that well. We have people using devices in multi-hundreds of megahertz, but those tend to be resonant applications. And the FT of our devices range anywhere from 2 gigahertz to 10 gigahertz.
I will add to that comment. The gate driver becomes a very critical component of that. You must have a good gate driver. It must be intimately coupled with the FET, and it is going to become a significant portion of your heat generation too at these frequencies. So you have to make sure you also manage the thermal aspects of it when you go to those high frequencies.
Okay.
But write to us if you do these hard switching at 100 megahertz. Love to hear from you.
Okay, we have a specific question about slide 17. It says, in slide 17, which is the switch Q1 that was used, which switch Q1 used the device with higher blocking voltage? For the 3-level flying capacitor converter, each switch takes half of the input voltage.
I can answer that one.
Okay.
When you first power up the circuit, V in will be higher than the blocking voltage of any of the FETs. And since the flying capacitor at that point will be at 0 volts, the Q1 will see the full voltage of the input. And that's why we make the upper FET full voltage rated capable, is so that when you have this situation with a low voltage on the flying capacitor, you don't destroy the FET.
Okay. Next question. For the 3-level buck, did you test efficiency to higher currents, for example, 20 or 25 amps? And how, if so, how is the efficiency at that high of a current level?
I'll say this much. Yes, we did test it. We tested it up to 25 amps. Efficiency loses meaning at that point because the converter will only allow itself to operate for 2 milliseconds before turning off. It is a feature that is designed for overcurrent operation. Your ripple voltage on the flying capacitors become very high, and it is merely meant to ride through a very short period of overcurrent. That is why the current is only given, the efficiency is only given at up to 12.5 amps. At 150% or around 17 amps, the converter will operate for 10 milliseconds and so forth. So there is a derating guideline, but because the converter operates in such a short period of time, it has no meaning to give an efficiency number anymore.
Is the 3-level capacitor flyback design presented here patented or freely available for use, or is there any licensing fee involved?
I'm not aware of any licensing required on that.
The converter has been around for many years, has been published in many papers, even outside of EPC. So I'm not aware of any patent on that.
Okay. Can you please explain a little on how C-fly voltage is controlled in the 3-level buck?
Yeah, how about Andreas? You want to try that one?
Yep. So there's a voltage divider which allows the microcontroller to continuously monitor the voltage across this flying capacitor. So we look at peak and valley values, try how just analyzing how symmetrical this voltage is. And depending on the distortion or the shift we find, we are modulating one duty cycle, making it a little bit longer, shortening the other one. So this is a fairly simple filter. I think at the moment we use something like a slightly tweaked single pole filter that feeds that information. So basically the peak information, peak and valley information from that voltage through that filter, and produces a correction factor for the PWM in every single control cycle. And the control loops then just pick up that parameter, incorporate it in their most recent control output result, and write it to the registers.
Okay. Can the 3-level converter be used for high conversion ratios such as 48:1 or even 48:0.6? What are the limitations?
Michael, you want to take a crack at that?
Sure, yes. The short answer is yes. They have been successfully done. There is a group at the University of San Diego that have published papers on going from 48:1 or even lower, as high as 240 amps. I believe they're going to even higher currents. They use a combination of flying capacitor, switch capacitor, and hybrid buck within the converter to achieve that. There's many advantages to doing that, but the most important advantage of that is that your effective duty cycle on the switches become higher, and that allows you to have the resolution you need for transient operation for the output down to 1 volt. So the short answer, yes, you can do it. There's a bit of work in it, and there's some papers that if you want to contact Renee or Rick, we can direct those papers to you
or just go to our website. And I think on our website we have a 48 volt to 1 volt converter from the folks at University of San Diego, and it's running 91% efficient. So that is definitely a good application.
Okay. 2 related questions about magnetics. So which magnetic materials are suitable in the megahertz range? Can you comment on inductor selections for megahertz converters, and what suppliers offer inductors with core materials suitable up to megahertz and beyond?
That's a good Michael question.
I feel like I get the short straw here. Yes, there are at the megahertz range, and for high efficiency converters, we found that the ferrite type materials are pretty well suited. The reason for that is they offer higher permeabilities, and the higher permeability allows the significant reduction in the conduction losses from the windings themselves. We have worked with both Coilcraft inductors, Vishay inductors, and in this particular project with both Worth Electronic and with Syntec on the inductors, they've done the custom inductors that are used on these boards. They also both use the ferrite-based materials, and on our other projects, we also work with Hitachi on the ML91S material, which is very suited, highly suited for use in the 1 to 2 megahertz range, and we've had some very high success used in the transformer there. So there are a lot of options for the magnetics, but at the higher frequencies, it looks like the ferrite-based magnetic materials are offering higher efficiency solutions.
Okay. Let's see. Are noise characteristics of the DS PIC available, such as voltage reference noise, comparator jitter, etc., which would add noise modulation to the buck converter?
Yes. So there are a couple of different implementation methods, but the DSPIC basically uses something like a random noise generator. which can be tuned and adjusted and then applied to very specific signals. So it's not a general frequency jittering that lets everything jitter, because especially if you're jittering the time base of a signal generator, for example, that would influence the control loop. So the control loop would try to set up a certain duty cycle, and then the duty cycle gets jittered by some peripheral engine, and then suddenly the timing that's considered to be known by the control loop is then kind of off. So incorporating random noise into the control output turned out to be significantly better and better controllable. So this is kind of a preferred method. But there are a couple of application notes on our website on the subject, where we compare different implementation modes, chaotic modulation, sinusoidal modulation, triangular modulation, and so on. And you could then analyze which is the best one for a specific application or to troubleshoot a very specific EMI issue.
How is the flying capacitor balancing loop made out of a current feedback signal in the 3-level topology?
So the flying capacitor control loop is only looking at the voltage of the flying capacitor. So we have this 2-level control system with an outer voltage loop and an inner current loop, and that is a straightforward average current mode control. The specific implementation of in that system is that we basically have this doubled frequency of the inductor ripple current. So we need to know exactly where we want to measure the current. So we have one pulse which is generated for one half bridge, basically in one operation. So we know exactly where the midpoint of the first current slope is. So that is the midpoint we are tracking. So this is how we are tracking the average current across multiple cycles. And we can look at the first and the second cycle within one switching period. So the same points are then the ones where we look for the voltage levels of the flying capacitor. So this is where we find either the peak or the valley, or let's say the positive and the negative maximum amplitude value of this flying capacitor voltage. So, and by comparing these values, we can detect some imbalance in the charging current of the flying capacitor. So the difference between these 2 points are then turned into a correction factor. So this difference is then basically inverted and applied or added to the control output of each of the duty cycles. So that we are making one duty cycle a little bit shorter. Let's say the positive charge time is made shorter, and then automatically the negative charging time is getting a little bit longer. And this then is balancing out the voltage across the flying capacitor as well as the ripple current in each of the cycles.
Okay. So we have a follow-up question to the noise questions, because he says, I think we misunderstood the question.
Oh, okay,
they want to know, what is the noise contribution from the on-chip voltage reference or the comparator jitter to minimize switching cycle and duty cycle jitter? We would like to quantify these
other way
effects.
around. Okay, so what is actually the noise level that's generated by the chip? Sorry, I misunderstood this question. Yeah, so we have detailed data on that in our data sheets, but you can assume, so the PWM logic is based on a 4 gigahertz base clock. There are some internal PLLs which take a 500 megahertz frequency, which is generated and then just multiplies it up to 4 gigahertz, giving us a 250 picosecond resolution. So there are a couple of dependencies on how much, so how stable your input voltage is, how many peripherals you have running. So basically the digital noise that's produced by the device itself. There are a couple of dependencies on how many AD to D converter cores you have on one device and how many of them are running. But eventually you can say it's roughly something like 3 LSB, 2 to 3 LSB jitter in that time base. So it means you have a very sharp Gaussian distribution of that specific timing you have set, where the median of the Gaussian distribution will be exactly at the timing you have programmed with a resolution of 250 picoseconds, and then the total jitter range would be somewhere in the range of maybe a nanosecond, slightly above a nanosecond maximum. From the A to D converter, it's basically the same. So a lot of that depends on the quality of your of the supply voltage that comes from the auxiliary power supply. So when you have a nice supply with very little noise, then you will achieve higher accuracy and less noise in the ADC. So all the analog voltages on the chip are kind of dependent. I mean, there's a little bit of filtering on the chip, but nevertheless, if you have a very noisy power supply of the DSPIC, then this will definitely influence your A to D converter. So one of the design challenges is then always when you build, especially when you build converters in that small size form factor, obviously the switching frequencies and all the disturbances and all the injected noise that is generated by the power supply itself will also show up somewhere in the supply lines of the microcontroller. So a little bit of filtering, a little bit of care of that is definitely required, but usually most of that high frequency noise is easily filtered by the decoupling caps. So the specific details about accuracies and dependencies can be found on our website. So the datasheet gives you, let's say, basically everything that's coming out of the chip itself. But there on top, so design-specific dependencies are also covered by an app node, so what we call low noise design. And this is in particular tailored for power electronics applications and specifically for switch and power supply designs.
And Andreas, I put up on the screen here the Microchip University here for training, which I highly recommend to anybody in the audience. You know, doing digital design, digital power control is it's a science, but there's art getting there. And I know that the startup time can greatly be minimized by going through the training that you provide.
Sure. And yeah, so if you follow one of the links, especially the first one, getting started in digital power, I think this is the best starting point. You will find a lot of information there: app notes, reference designs, devices, demo boards, and so on. And I think that should be a good starting point where you can find your way into the topic. And if you look for specific training, then the Microchip University. So this is something that was, now basically due to COVID, is a new platform we have just installed. So we're still in the process and continuously adding classes, and that is not only covering power supply topics, so it's very broad. So you can find all kinds of topics around microcontrollers and other applications. But the power supply training program there, which we currently build up, consists of roughly 12 different sessions at the moment, starting from very simple, what is a power supply, what is an inductor kind of class, going into analog control, hybrid control, and then full digital control, and then into application-specific topics, like also gallium nitride high-speed designs and design challenges, but also more AC to DC related applications like total voltages, PFC designs, and so forth. So if you're interested, check it out, and I hope you find it helpful.
Great. Okay, here's the next question. How do you measure high current devices handling more than 40 amps? Do you use a device analyzer like Keysight, or do you measure by making a separate circuit?
Michael, you've been struggling with that your whole life. You're on mute, though.
Yeah, sorry.
Is that intentional?
It actually is very difficult to directly measure the current in the FETs. First of all, we have a lot of information on how we do that in our LiDAR applications. Usually what happens is we have to measure the currents in the rest of the circuit. For example, in the buck converter, you'll measure the current in the inductor. And based on all the analysis work you've done up front, through simulation, etc., then you will know what the current is in the FET. You don't always know 100% in that case, but the challenge with current measurement is that it will inevitably inject inductance, and that is usually not a friendly parameter to have for your FET. So when it comes to measuring high currents, you have to be very cognizant of the addition of the inductance, and I would strongly recommend to go through our app notes on how we do that for LiDAR applications, because we address both the low inductance for the measurement using a shunts, and also how to compensate for that inductance that's in the shunt and measurement, so you get a very accurate reading.
Okay, is the flying capacitor bidirectional? Could it be used as a boost converter?
Fundamentally, there's no reason why it cannot be done like that. I've seen topologies where only the two bottom FETs are installed. The two upper FETs in our circuit would be replaced with diodes, and it's configured as a multi-level boost converter. So I would say the simple answer is there's no fundamental reason why it cannot be used as a boost converter.
For the 3-level topology, is it really suitable for high current applications? If high current flows through the flying capacitor, wouldn't you have to use many ceramic capacitors in parallel, but this would lead to a very large size converter?
There you'd have to look at the voltage of the capacitors, and the lower the voltage of the capacitors become, excuse me, the higher the capacitances that you can choose for those flying capacitors. If you look at the work done by the folks at the University of San Diego, they are scaling the voltages all the way down to 1 volt, and they still get pretty reasonable voltage ripple across their capacitors, because as they're scaling down the voltage, they're also scaling up the capacitance respectively. So it's a matter of design, it's a matter of understanding how the topology works and what you want to achieve.
Okay. How is the adoption of GaN in the market today and the future 3 to 5 years? Are there any additional challenges for laptop makers to solve to adopt GaN?
Yeah, so GaN is rapidly being adopted in many applications associated with computers. One of the biggest where we've seen a lot of success is in LLC converters on servers that now have brought 48 volts onto the server board, and those are very high volume applications. And I think everybody's converting to that over the next couple of years. In terms of notebook and laptop and desktop computers and displays, a lot of those use a 19-volt bus, and it's a good place for GaN, but many of them are going to quick charging configurations so that you can pump a lot of current in a very small period of time and recharge your computer, like now is available on many cell phones. And for those, there's a move to go to a 56 or even higher voltage input into the notebook computer with a down converter to 19 volts inside the computer, and that was the fundamental application that we developed these boards for. I think over the next few years you're going to see more and more of that, also in very thin displays. Are they in volume production yet? No. But I would expect maybe by the end of 2021 they will be. And GaN is being adopted also very rapidly. I'm sure many of you have seen these little tiny AC adapters for 65 watt and 100 watts even now that use GaN at the primary side and GaN at the secondary rectification side for USB-C PD applications.
Is there an application available for the 9148 that covers the control loop implementation? I think that maybe means application note.
Yeah, so Michael, do you have the control loop implementation in the app note that you have for the 9148? And if not, where do we go to get it?
The control loop, all the controls are well documented in the source code. that is available through both EPC and Microchip's websites.
So you can download it off the website if you go to the landing page for 9148?
Yes.
Excellent.
I think so. In the first release of the firmware, which is currently available, you would really have to look into the source code to find this documentation. So we have scheduled for let's say end of the first week of January to update the current release of that firmware on the website and provide a fully blown firmware documentation, which hopefully should make it a little bit easier to understand the control loop implementation.
And let me just put that up here on the screen. Hang on one second. I got this.
I'll also add to that in this slide presentation we presented today, you've got the overview block diagrams of the control system, so you can see it graphically, which is, in my opinion, easier to understand for human beings.
Okay, and these are Microchip website references that you might find very useful.
Is there an application note for 75 megahertz switching frequency?
No, we don't have one at that high of a frequency. That's a customer application.
Right.
Okay. Okay. Good.
By the way, I would like to point out that there are applications that we do either have or will have very soon at 100 and 200 megahertz, but those are lighter applications. So those are pulse trains that are running at those frequencies. So I don't know if that's useful or not.
I think what it does show is the importance of the relationship of the connection between the gate driver and the FET itself, and how much power between the two devices are exchanged, because at those very high frequencies, the gate driver also works very hard. And so I still think they are good references.
It appears that you have both ceramic and polymer or tantalum input and output capacitors. Can you comment on capacitor choices at high frequency?
The capacitors we choose for high frequencies primarily the ceramic capacitors, mainly because they have the low inductance. The only reason why we have the polymer capacitors, the tantalum polymer on the board itself, is because they offer high capacitance. That was needed for two reasons. One is for the input to stabilize the voltage of the converter, and the same reason on the output. You need to have sufficient output capacitance in order to ensure that you have stable control parameters. So the high frequency ceramic capacitors are used for the high frequency and to filter out, and then the large value polymer tantalum capacitors are used for the bulk of the capacitance at the lower frequencies.
I think we probably have time for just one more question. You're mute.
Sorry, it was a good one too. Can you comment on GaN applications in linear region like hot swap circuits where wide SOA would be required?
All right, Michael.
I would say that we've done a number of experiments on the SOA, and we've found some very surprising results of how robust they really are at those extreme conditions. So I think that I'm not 100% sure on your question, but if I understood it correctly, the safe operating area we put into our data sheets as well, and the GaN devices have been tested repeatedly and quite robustly, even exceeding those numbers, and they've proven to be pretty reliable in that area.
Okay. All right. Well, that pretty much takes us up to the end time here. So thank you, Alex. Thank you, Andy. And thank you, Michael, for joining us today. And thank you to everyone in the audience for attending. If there are any additional questions, please feel free to send them in to info@epc-co.com, and we will get those to our panelists to answer. Once you leave today's webinar, you'll receive a survey on the presentation. So we would very much appreciate if you can take the time to complete that and provide your feedback. And you will also receive an email within 24 to 48 hours with a link to view a recording of today's webinar. So thank you again for joining us today. We hope to see you at the next webinar. Visit us at epc-co.com for more information on that, and have a great rest of your day. Thanks again, everybody.
Thank you.